Hi, in this week we will talk about different methods to align images that share some characteristics. So far we have performed operations that change the pixel values on an image, and in a general way we can call this image filtering. However, there is a different set of manipulations that will be useful to perform several methods on computer vision. These are transformations that actually can change the shape of the image. For example, in previous videos we have mentioned the term warping, but we haven't properly defined those operations. The main difference between image filtering and image warping is that in the first one we are applying a transformation to the pixel values, while in the second we are applying the transformation to the location of the pixels. In other words, we are manipulating the coordinate system of the image. So let's start with the basics. For example, scaling the image. So we have our initial image and we want to scale it by a factor A. We can represent this transformation T in a matrix form. In this case, the initial image has coordinate x1, y1, and we want to find the transformation that results in x2, y2. In this particular case, T is a 2 by 2 matrix that contains the scale in the diagonal. If we wish, for example, to scale the image using different values for x and y, we can change those values in the matrix T. Of course, if we want to revert this effect and reduce the size of the resulting image, we can apply the inverse transformation to the second image, and we will obtain a duplicate of the original one. Now let's see the rotation. If you remember from last week, any point can be represented by its angle theta and the distance r with respect to the origin. Then we have that x equals to r cosine of theta and y is equal to r sine of theta. If we want to move P1 to P2, we can add the components in this way, which we can write in the matrix form in this way. So, in the same way that we did with the scaling, we can invert the matrix T to obtain the opposite effect. We can also transform the image in just one dimension at a time. This is called skew. And as you can see in the matrix T, M is the parameter that will control the amount of the transformation. This can be also applied to the vertical axis by changing the position of M. In all these 2 by 2 transformations, the origin of the resulting image will be the same that in the original image. And because the transformation is linear, all lines will result in lines. And all lines that are parallel will result in parallel lines in the new image. So now let's increase the difficulty a bit. Imagine that we want to change the origin of the image because we are trying to align the images. So we need to translate the image from its origin so it overlaps with the target image. In this case, a 2 by 2 transformation matrix is not enough. We are going to use the homogeneous representation. This only means that we will include an extra dimension to our transformation matrix. Then we can say that x is equal to x tilde divided by z tilde, and y is equal to y tilde divided by z tilde. Here, z is just like a dummy variable that should be different from 0. Usually it's 1. Now, to translate the image, we just need to add the distance to the correct dimension. For example, here we are translating the origin by tx and ty. And we can write this in the matrix form using the homogeneous representation in this way. Here we have that x2, y2 is equal to x1 y1 multiplied by the transformation matrix, in which we include tx and ty. This form of the transformation matrix is really common. If you remember, we used it on the video of uncalibrated stereo, where we talk about rotation and translation. Well, it turns out that you can represent all 2x2 transformations using a 3x3 matrix. And the nice thing of this representation is that if you need to apply several transformations to an image, instead of multiplying the image several times, you can just multiply the different transformation matrices to combine them, and then just apply one to the image. And of course, the inverse of the matrix will revert the effect. All these transformations have something in common. If you see the lower row of the matrix is always 0, 0, 1. This family of transformations is called affine and has the characteristic that the origin in the resulting image does not necessarily map to the original one, but still parallel lines in the original image will result in parallel lines in the resulting image. Finally, if we modify the lower row in the matrix, then we get a projection matrix. But you already know what is a projection matrix. That row will project the image of one plane to another. We already saw this form. The lower row will project the image of one plane to another. We use it to find the projection from one camera to another camera in a binocular system. The characteristics of a projection matrix is that the origin of the resulting image does not necessarily map to the origin of the initial one. And lines still result in lines. However, parallel lines does not necessarily remain parallel in the resulting image. Okay, in this video, we review different types of image transformation. We review the affine matrix and the projection matrix. See you in the next video.